To begin, a neural network is a computational model inspired by the structure of the human brain. It's made up of interconnected nodes, called artificial neurons, that work together to process information. These networks can automatically learn from data. They find patterns, make predictions, and even improve with experience, just like we do when we learn from mistakes. Instead of being explicitly programmed, they learn by adjusting internal connections called weights. That's what makes them so powerful. Slide 3. Brain analogy. Biological. Now you might be wondering, why is it called a neural network? The answer lies in biology. This diagram shows how biological neurons in your brain actually work. When you see, think, or learn something, signals travel through networks of connected neurons. A signal enters through the dendrites, these branch-like structures you see here. It travels through the cell body, down the axon, and then crosses to the next neuron at a junction called a synapse. This is where real learning happens. The strength of these synaptic connections changes based on experience, allowing your brain to adapt and remember. Artificial neural networks were literally designed to mimic this biological process. Neural networks are machine learning models inspired by the human brain. They consist of interconnected nodes, neurons, that process information, learn from data, and make decisions. Just like the brain, neural networks enable tasks such as pattern recognition, prediction, and decision-making. Key idea: artificial neural networks mimic how biological neurons communicate and learn through experience. Neural networks are inspired by how the brain works. A biological neuron receives electrical signals through dendrites, processes them in the cell body, and if the signal is strong enough, it fires through the axon. Similarly, an artificial neuron receives numeric inputs, multiplies them by weights, adds them together, and then decides whether to fire or not, using a mathematical function called the activation function. In both cases, learning happens by adjusting connections. In biology, it's synaptic strength. In AI, it's weight adjustment. Here's a quick comparison between the brain and an artificial neural network. The neuron in the brain corresponds to the processing unit in AI. Synapses, which connect neurons biologically, are like the weights in an artificial network. Firing a signal is equivalent to activating a neuron. And finally, biological learning, adjusting synapses through experience, mirrors how neural networks update their weights during training. Biological neuron receives signals, processes them, and fires if strong enough. Artificial neuron receives numerical inputs, multiplies them by weights, sums them, and applies an activation function. Both systems learn by strengthening or weakening connections. Synapse. A synapse is basically an input signal to your neuron. A synapse is also known as a connecting link. Every neuron in a neural network expects a set of synapses. Neural networks can be categorized based on their architecture and application. The perceptron is considered the foundation of neural networks. It's a very simple model that learns to map inputs to an output, typically to decide between two classes, like 0 or 1. It does this by adjusting internal parameters called weights and a bias to reduce errors during training. There are two main types of perceptrons: the single-layer perceptron, which is the simplest form, and the multi-layer perceptron, which extends it by adding hidden layers to learn more complex relationships. I'll explain each type in more detail in the next slides. Single-layer perceptron learns linearly separable patterns, suitable for simple classification tasks, struggles with non-linear relationships. Multi-layer perceptron, MLP, contains 2 or more layers, handles complex non-linear patterns, foundation for modern deep learning models. The single-layer perceptron is the simplest form of a neural network. It takes multiple inputs, calculates a weighted sum, adds a bias, and passes the result through an activation function, usually a step function, to produce a binary output. This model works well for problems that are linearly separable, such as the AND or OR logic gates. But it can't handle nonlinear patterns, like XOR, because it doesn't have any hidden layers to capture complexity. The network learns by updating its weights and bias according to the perceptron learning rule, which adjusts parameters based on the classification error. The multi-layer perceptron, or MLP, extends the single-layer model by introducing 1 or more hidden layers between the input and output. These hidden layers use nonlinear activation functions like ReLU, sigmoid, or TON, which allow the network to learn complex, nonlinear relationships in data, including problems that the SLP cannot solve, like XOR. MLPs are trained using backpropagation and gradient descent, where errors are propagated backward through the layers to update all the weights efficiently. In fact, The MLP is the foundation of many modern deep learning architectures we use today. A typical neural network is composed of three main layers. Let's compare directly. An SLP has two layers, uses a step function, and is simple but limited to linearly separable tasks. An MLP has three or more layers, uses nonlinear activation functions like sigmoid, ReLU, or TON, and can solve complex nonlinear problems. That's why MLPs are used for almost everything: image classification, NLP, game playing. The activation function is the game changer. Nonlinear activations enable the network to learn complex representations. Without them, stacking layers wouldn't help. You just have a linear transformation. Now that you understand the structure of neural networks, let's talk about what actually makes them learn: weights and biases. These are the two parameters that the network adjusts during training. Weights determine how much influence each input has on a neuron's output. Imagine you're making a decision. Some information matters more than other information. Same here. If a weight is large, that input has a big impact. If it's small, that input doesn't matter as much. A weight can be positive or negative. Negative weights mean the input inhibits the neuron. Positive weights mean it enhances the neuron. Bias is equally important, but it works differently. Bias allows the neuron to shift its activation threshold. It helps the network fit the data better. Here's the key. Both weights and biases are what the network actually learns. When we train a neural network, we're really just tuning these parameters. We start with random weights and biases, then gradually adjust them based on prediction errors until the network performs well. During training, we ask, given the error, which weights should we increase? Which should we decrease? How much? That adjustment process is the heart of learning. So now let's trace what happens when data enters the network. This process is called forward propagation. Forward propagation has two steps per neuron. Step 1. Linear transformation. The neuron receives inputs. It multiplies each input by its weight. Remember, weights determine importance. Then it adds all those weighted inputs together. Finally, it adds the bias, which gives the neuron an adjustment lever. Mathematically, Z equals W1, X1 plus W2, X2 plus WX yours plus B. This is just inputs times weights plus bias. Simple multiplication and addition. This is what we call the weighted sum, or the Z value. Step 2. Activation. Here's where magic happens. That Z value is fed into an activation function, a nonlinear function that introduces complexity. The activation function determines the neuron's final output. So the flow for each neuron is inputs, right, pointing arrow, multiply by weights, right, pointing arrow, add bias, right, pointing arrow, pass through activation function, right, pointing arrow, output. And this happens at every neuron in every layer. The output from one layer becomes the input to the next layer. Why is this called forward propagation? Because the data literally moves forward through the network in one direction. Input layer, right pointing arrow, hidden layers, right pointing arrow, output layer. Point to the diagram on the right. This diagram shows the process. Inputs X1, X2, X yours come in. Each gets multiplied by its weight, W1, W2, W0. They sum together. The bias is added. Then the activation function F processes it. Finally, you get output Y. This forward pass is fast. Once you have weights, you can calculate an answer quickly. This is why neural networks can make predictions so rapidly once trained. We mentioned activation functions in forward propagation, but they deserve their own attention because they're fundamental. What is an activation function? It's a mathematical function applied to a neuron's output. It takes the weighted sum Z and decides what the neuron's final output is. Essentially, it decides, should this neuron fire? How strongly? Why do activation functions matter? Why can't we just use weights and bias? Great question. Here's the critical insight. If you only multiply inputs by weights and add bias, you're doing linear math. Linear functions have a property. If you stack them, you still get a linear function. So a 10-layer network would be mathematically equivalent to a 1-layer network. All that depth would be pointless. Activation functions break linearity. They introduce nonlinearity into the network. This is what enables a deep network to learn complex, nonlinear patterns. Without nonlinear activation functions, neural networks would be as powerful as simple linear models. With them, you unlock the true power of deep learning. Popular activation functions. We have several to choose from. ReLU, rectified linear unit. This is the modern default for hidden layers. It's fast and works exceptionally well. Sigmoid outputs values between 0 and 1, so it's natural for probabilities. Often used in binary classification. Tan, hyperbolic tangent. Similar to sigmoid, but outputs between -1 and 1, so it's zero-centered, which can help training. Each has different properties. We'll look at a couple in detail, but the key idea is activation functions introduce nonlinearity, and that's what makes deep learning work. Delivery notes. Let's look at ReLU in detail since it's the most popular. What does ReLU do? ReLU stands for Rectified Linear Unit. The idea is remarkably simple. If the input is positive, output it as is. If the input is 0 or negative, output 0. That's it. The formula looks fancy. F of x equals max, 0x. But it just means keep positive values, eliminate negative ones. Point to the graph. See this graph? It's a straight line at 0 on the left, for negative values, then goes up diagonally on the right, for positive values. That knee at 0 is where the nonlinearity happens. Why is ReLU so popular? First, it's computationally efficient. It's just a simple comparison. Is x greater than 0? That's it. No complex math. Second, it avoids the vanishing gradient problem. Other activation functions like sigmoid can cause gradients to shrink during backpropagation, making learning slow or stop. ReLU mostly avoids this. Third, it's simple enough that it works well, but effective enough that deep networks train much faster with it. When do we use ReLU? Primarily in hidden layers. It's the default choice in modern deep learning. If you're building a network and don't know what to use, ReLU is almost always the right answer for hidden layers. One drawback: ReLU kills all negative values. So if your network has truly important negative information, you might use a variant like leaky ReLU that preserves some negative values. But standard ReLU is the workhorse. The sigmoid function is used to decide how much a neuron should be activated. It takes any number as input and turns it into a value between 0 and 1. If the input is a big positive number, the output will be close to 1. If the input is a big negative number, the output will be close to 0. That's why we often use it when we want the result to represent a probability. For example, deciding if something belongs to class 1 or class 0. But the sigmoid also has a drawback. When the input is too high or too low, it stops learning well. This is called the vanishing gradient problem. Even with that, the sigmoid is still important because it helps the network learn nonlinear patterns, not just straight lines. The softmax function is mostly used in the output layer of a neural network when we have more than 2 classes to predict. It takes a list of numbers, the raw outputs from the network, and turns them into probabilities that all add up to 1. The class with the highest probability is usually chosen as the model's final prediction. For example, if we're classifying images of animals, softmax might give cat, 70%, dog, 20%, horse, 10%. That means the network is most confident that the image is a cat. Softmax helps the model not only choose the right class, but also show how confident it is in each choice. 1. Step/linear, perceptron. Used for simple binary classification, e.g. and OR. Output is 0 or 1. 2. Sigmoid. Used when you need probability outputs between 0 and 1. Common in binary classification, logistic regression, binary neural nets. 3. Softmax. Used for multi-class classification problems. Converts outputs into class probabilities that sum to 1. 4. Linear. Identity. Use in regression tasks where output is a real value, e.g. price, temperature. Mike SimpleScript. When to use activation functions. Activation functions decide how a neuron behaves and what kind of problem the network can solve. If we have a simple binary problem, like yes or no, we use the step function. If we want the output to represent a probability between 0 and 1, we use sigmoid. When there are many classes to choose from, like cat, dog, or horse, we use softmax. And if we want the network to predict a number, like a price or temperature, we use the linear activation. So the choice of activation function depends on what type of output we want the model to produce. Recurrent layers, Tan/sigmoid/ReLU. Sequence modeling. Training happens through 5 steps repeated many times. First, forward propagation computes predictions. Second, we calculate loss, how wrong the predictions are. Third, we compute gradients, the direction and magnitude each weight should change. Fourth, we update weights using gradients. Fifth, we repeat on more data. Each cycle, Weights move closer to optimal values that minimize error. That's how learning happens. Not through luck, but through systematic gradient-based optimization. Loss functions measure the difference between predicted and actual output. They guide weight adjustment during training. MSE is for regression tasks. Cross-entropy is for classification. Think of loss as the error signal that tells the network, you're wrong by this much. Hebb's rule is one of the oldest learning rules in neural networks. The main idea is simple and famous. Neurons that fire together, wire together. This means, when an input neuron and an output neuron activate at the same time, the connection between them gets stronger. Hebbian learning is unsupervised. There's no teacher, no target output. The network just reinforces patterns it sees repeatedly. The rule itself is very simple. Delta W equals alpha times input times output. So if the input is active and the output is active, the weight increases. If one of them is 0, nothing changes. This rule basically helps the network learn associations. When two things happen together, their link becomes stronger. Where? ETA right pointing arrow, learning rate, controls update speed. T, right pointing arrow, target output, desired result. Y, right pointing arrow, actual output, predicted result. T minus Y, right pointing arrow error, difference between target and prediction. X underscore I, right pointing arrow input value. Asterisk. Now let's compare the main learning rules used in neural networks. We have 3 key rules: Hebbian, perceptron, and delta. Hebbian is unsupervised. It doesn't need a target output. It simply strengthens connections when neurons activate together. The perceptron rule is supervised. It updates weights only when there's a classification error, but it does not consider the activation function's derivative. It's mainly used in single-layer networks. Finally, the delta rule is also supervised, but it goes further. It uses the derivative of the activation function to guide weight updates. This allows it to train single or multi-layer networks effectively. Gradient descent is the general optimization method used in neural networks. It takes the idea from the delta rule and extends it to more complex models, like multi-layer perceptrons. The idea is simple. We compute the gradient, which tells us how the loss changes, and then we take a step in the opposite direction to reduce the error. The update rule is new weight equals old weight, learning rate times gradient. Small learning rate right pointing arrow slow but stable steps. Large learning rate right pointing arrow fast, but might overshoot. So gradient descent is the backbone of learning in neural networks. And it's exactly what allows backpropagation to work. Right arrow transition. Now that we understand gradient descent, we can move to backpropagation, which applies it across all layers. A derivative measures how much the output changes when the input changes, basically the slope of the function. In neural networks, it tells us how strongly a weight should be updated. Large derivative right pointing arrow, big update. Small derivative right pointing arrow, small update. Zero derivative right pointing arrow, no learning. That's why derivatives are essential for gradient descent and backpropagation. Before we move to backpropagation, it's important to know that gradient descent comes in different versions depending on how much data we use in each update. The first one is batch gradient descent, where we use the whole dataset every time we update the weights. It's very accurate, but slow for large datasets. The second type is SGD, stochastic gradient descent. Here we update the weights, using only one data point at a time. This makes learning much faster, but also noisier. Finally, we have momentum, which adds a fraction of the previous update to the current one. It helps the algorithm speed up in the right direction and avoid getting stuck. These variants don't change the idea of gradient descent. They just change how we compute the updates to make learning more efficient. Batch gradient descent calculates the gradient using the full dataset, giving the most reliable update direction. We run a forward pass, compute the total loss, calculate the exact gradient, update the weights, and repeat until the loss stabilizes. Uses one training example at each iteration to update the weights, fast and efficient for large datasets. Introduces noise and updates right pointing arrow helps escape local minima. Update rule. W underscore new equals W underscore old minus eta underscore WJ WM X underscore IM Y underscore I. Converges quickly, but may show high variance in the loss curve. Momentum adds a fraction of the previous gradient to the current one, acting like inertia. This smooths noisy updates, reduces zigzagging, and speeds up convergence. The only drawback is that the momentum coefficient has to be tuned. Backpropagation is the main algorithm used to train multi-layer neural networks. Its job is to compute the gradient of the loss with respect to every weight in the network, not just one layer. We need it because a single-layer perceptron can only learn simple, linearly separable patterns. Real problems require hidden layers, and the delta rule alone can't handle that. Backprop uses the chain rule to send the error backward through each layer, so every weight knows how much it contributed to the final error. In short, backpropagation combines gradient descent, the chain rule, and multi-layer architectures to train deep networks efficiently. Backpropagation is the core algorithm that allows multi-layer neural networks to learn. It efficiently computes the gradient of the loss function for every weight in every layer using the chain rule. This is necessary because single-layer perceptrons can only learn linearly separable problems, while real-world tasks need hidden layers. Backpropagation essentially combines gradient descent with the chain rule to propagate error backward through the network. The training cycle follows 4 steps: forward pass, error computation, backward pass, and weight update. This algorithm is the foundation of modern deep learning. https://www.youtube.com/watch?v equals dh-nuvom3l3s. The accuracy is 75%. In the perceptron, we use a very simple type of activation function called a step function, or sometimes a linear threshold function. Here's how it works. The perceptron takes the inputs, multiplies them by their weights, adds them up, and compares the result to a threshold. If the result is above the threshold, the output is 1. If it's below, the output is 0. So basically, the perceptron makes a binary decision, yes or no, 1 or 0, which is why it's used for binary classification problems like AND or OR logic gates. https://www.youtube.com/watch?v equals dh-nuvom3l3s. The accuracy is 75%. Small diamond and right pointing arrow, both true small diamond OR, right pointing arrow. At least one true small diamond XOR. Right pointing arrow. Only one true.
Activation égale sigmoïde Fanck.
Momentum is a parameter used to speed up the learning process. Learning rate is set by the user, 0.1, 0.01, very small. We need to define the number of epochs for this calculation equals number of times to do these calculations.